In this video, I will be explaining to you my codes of creating a VPython simulation of a ball's freefall projectile. So this is how it would be looking like. This is the simulation that we're going to make. Okay, so to start up, we have to start with this line from VPython import. So this is just declaring that we're using the VPython module, and every program should start with this line. And then we're going to set some physical constants that we're going to use later on. So first of all, the g is 9.8 meters per second square. The size, which is the ball radius, will be 0.25 meters. The height, which is the ball center initial height, will be 5.0 meters. And right here you can see me adding some remarks to my code. So by doing so, you just need to put a hash mark, a hash symbol, and then all the text after the hash symbol will have no effect on your code. So adding remarks can really help your codes be clearer, especially if you want to review it later. Okay, so now let's start with just setting some background. So it's like you're creating this simulation world. You have to have some backgrounds first. So of course we're going to set a scene, and this is how big it is. The 800 is in pixels. The center is where it is. And this is a vector, so these are the x, y, and z axis. And the x-axis, positive, x will point to the right of the screen, the y to the top of the screen, and the z outward from the screen. In the background, we'll set the color for it. So these three numbers represent red, green, and blue. And if you don't type in the background, your scene will just be black. So the scene is this square you can see right here. And then we're going to set the floor. This is how big it is, and it's blue. So it is this blue box underneath. And then of course the ball, which is the main character in this simulation. And the radius is equals to size. The size is a variable that we had assigned earlier on, which is 0.25 meters here. Its color, and this make trail true means that I want the trail to show after the ball start moving. So it is this red line here. And the trail radius is trail is, which is 0.05 meters here. And this line shows that at the beginning of my simulation, you will see the on the screen, and this is where it is. So now we're done with setting all the backgrounds. So now we're going into the physics details. So first of all, we need to give the ball's position an initial center position. So this is where the ball will be initially, and the height, again, is a variable that we had assigned earlier. And this is the ball's initial velocity, which is 6, 8, and 0. Okay, so we're going to use a while loop to simulate the ball's motion. So first of all, we will set the time step at 0.001 second. So time step basically means that we're going to divide the whole projectile motion into several 0.001 second steps. So every value we yield would be for that exact period of time. So for instance, at first we will have the ball's initial position, and then we will have its position at 0.001 second, and its position at 0.002 seconds, and etc. And then we'll connect the dots. So the time step is related to the rate. Rate means how many times the loop runs in 1 second. So if I rate 1,000, it means that this while loop will run 1,000 times every second. So if then represents 0.001 second, and we run it 1,000 times every second, if we multiply these two numbers, we will get 1, which means the simulation will run at exactly the same real-world time. But say, if we change the rate to 500, the product of these two numbers will be 0.5. This means the simulation will be running at half the real-world time. Okay, let's change it back. Okay, and now let's look at this line. This sets the condition for which the while loop will keep running. So the ball position y means the center height of the ball. When the center height of the ball is bigger than its size, which is its radius, it means the ball is high above the ground. And when its center height is exactly equal to its radius, it means the ball has just hit the ground. So when the ball is above or exactly the time it hit the ground, the loop will be running. But once it hits the ground, the loop will stop running, and it will yield a final value for the position in the vector, in the velocity, which we will be talking right now. So for every time step, which is for every 0.001 second, the ball will be at a different position. So we will have to recalculate the position. So its current position will be its initial or its previous position, plus the distance it traveled in this period of time, which is its velocity times 0.00. And then, because it's a free fall motion, so the horizontal velocity will not change with time, but the vertical velocity will be affected by the gravity. So the current vertical velocity will be its initial vertical velocity minus gt, which is the acceleration over time. So these two are will keep changing through time, and it will give us the ball's current position and its current velocity. Okay, so after these being set, we can now calculate the displacement. So let me just assign another variable to be ball's position change, and it will be the ball's current position, which is the position that a while loop yields in the end, which is the position where the ball hits the ground. So it will be its final position minus this one. This one is the ball's center initial position. So for this equation, I will get that the ball's position change, which is its displacement, but in vector. But I want to know the magnitude of its displacement. So I want to change the vector into a magnitude. So this is what this line is doing. So now after I have converted the displacement into a magnitude scalar, I can print it on a screen. But first of all, if you remember, we printed out free fall on the screen in the beginning. So I have to make this message disappear. And then we have to print out different message, which is displacement. And you see a string right here. This means because the displacement that I yield right here, it's a value, it's a number. But I want to print it as a word, so string will convert it from a value to more like a word. So I print my displacement in meters. Yes. After we have done all of these, now this is how the simulation will look like right now. Okay, so the final thing we're going to do with this simulation is we're going to add an arrow to it. So first of all, we have to create the arrow object right here. So we set the color at green, and the shaft width just determines the thickness of the arrow, which is 0.005 meters right here. And of course, some of the initial stuff about the arrow. So the arrow's position means the center initial starting point of the arrow, and I want it to be exactly where the center of the ball is. So it's just the same as the ball center initial position. And the axis means where the arrow is pointing toward. So I want the arrow to be parallel to the velocity's vector and proportional with the velocity's magnitude. So this is what I do. I just take the velocity's vector and times it with a constant so I can make it shorter. So right here, as the ball's position is going to change with time, and I want the arrow to always be at the center of the ball, so the arrow's position, the arrow's starting point, also needs to change with time. It needs to always be the ball's current center position. And of course, the ball's velocity is going to change with time as well. So the axis is also going to change with time. So by doing this, I will make the arrow always parallel with the vector of the velocity and always in proportional to the magnitude of the velocity. So these these 4 lines are about the arrow. So now the simulation will look like this. So you see the freefall message at first, and then it will disappear and be replaced by displacement. And the green arrow is always proportional to the magnitude of the velocity and parallel to the velocity. So this is the end of the simulation.